Today we want to look at applications of exponential functions. Now before we start, I want to review something that I talked about previously, but just kind of in passing. We looked at problems where we had radioactive half-life, bacteria triples in 3 days, and we ended up with equations that looked like a 2x or a 3x. Now, what I want to show you is many times we don't use the 2x or the 3x. Instead, we convert everything to e. Now, 3x and 2x aren't a problem since our change of base formula that we just did in the previous lesson. But it's still, to make kind of uniform e, we can look at this. Now, to show you how this works, I'm going to get rid of the 3, and we'll look at just the 2x. If you look at this, this says e to the k raised to the x equals 2 raised to the x. So basically this is saying e to the k equals 2. And we get this crazy 0.6931471806 for k. How do we find that? Well, if we take this exponential equation and we write it in logarithmic form, this would just be the natural log of 2. And if you put the natural log of 2 in a calculator, you get our answer. So you can see that we can change everything to base e by just converting it from base 2 or base 3 or anything else. So let's look at our first type of problem. Exponential growth and decay. So our formula is a e to the bx or a e to the negative b. If it's going down or depreciating, my b is negative. This we did some problems similar as before. So here's my graph. If it's positive, it's going up. Here is negative coming down. So let's look at an example. The population is given by this formula, 4,450 e to the 0.02 t. So what is the population in 1970? Well, notice over here our scale. 1970 is 0, 1990 is 20. So we have 4,450 e to the 0.02, and we start at 0, which anything to the 0 power is 1, so that goes away. So that a is always our initial amount. And then they want to know when will it be 5,000. Now, we've already done these kind of questions, and since this is an e, we can solve it. And really it doesn't matter what our logarithm is anymore since we have our change of base formula. So I get e to the 0.02 t. I'm going to divide 5,000, divide by 4/5, and I get 1, 2, 3, 6. So I just divided both sides by 4,450. And then finally to solve, I need to write this in logarithmic form, which is the natural log of 1.126. And finally, I need to divide by 0.02. And if we figure out what that equals, natural log of 1.126, oops, there should be a 3 there, sorry, 36, divide by 0.02, we get 5.83. There should be a 3 right there from up above. So when will the population be 5,000? 5.83 years. So another one, depreciation. A new SUV is sold for $30,788 and has a book value of $24,000 2 years later. First off, we want to find the model. So in general, this is A, E to the B, T. Now remember, A is always the initial amount. A is always the initial amount because when you put in 0 for T, E goes away. So we know A is our initial amount, 3,788. Now I need to find my B by saying it equals 24,000 in 2 years. So I write my equation, E to the B times 2. Now I need to solve for B. So this is E to the 2B. Once again, I'm going to take 24,000 and divide it by 30, what is it, 788? Oh, I lost it. 24,000 divided by 37.8. So I get 0.7795. Now I need to solve for B. I need to write this in logarithmic form. This goes back to what we did previously. This is why it was important what we did last chapter. 2B is the natural log of 0.7795. So my B is natural log of 0.7795 divided by 2, which would be on our calculator 0.7795 divided by 2, negative 0.1256. 46, I should say. So there's my B. So here's my A, here's my B. So if I write my equation, this is 30,788 E to the negative 0.1246 T. You can see exponent's negative, that tells me it's going down. It's depreciating, here is the value. So if we want to say, what's the value after 10 years? I'm going to plug in 10. For my exponent. And let's put that in our calculator. 377. So this is very similar to what we did previously, but now we have to find the formula. Now my calculator, I don't need parentheses. Yours, be very careful. You have parentheses as the exponent. And we get 88,056.26. So after 10 years, the value of the car is $8,856.26. So on those problems, we've looked at problems where you're given the formula, and we know how to do most of that. We did a lot of that in the last chapter. Now we're going to be given problems where you're not given the formula, but you're given the initial value and then the value after some time, and you're going to have to figure out what A and B are. Now, if we go back and look at this growth model, this is the one we looked at before. And I said, what happens if T is 10,000? T is really big. We plug 10,000 in, and we get a rather large number. Understand, this number on the calculator is 3.22 times 10 to the 90th. A large number. And that makes sense. We did all the math right. But here's the problem. If you consider there are 10, probably fewer than 10 to the 80th atoms in the entire known universe. And our answer is 10 to the 90th. That's much bigger. So how can our population grow to something that's bigger than all the atoms in the known universe? It's not possible. It says here, some bizarro world where things just are all totally out of whack. Doesn't make sense. That's the problem with our exponential growth. It doesn't grow forever. Most of those classical exponential growth problems should really be not exponential growth, but logistic growth. And you notice here, exponential growth starts off and then just continues to ramp up. Notice logistic growth. It starts off very similar. If I would take this beginning logistic growth model over here, it starts off very similar. However, it reaches a point where it's still growing, but the growth is slowing down. And then eventually levels off. It doesn't grow forever. So here's our logistic growth model. Now this is a little bit more complicated. We're going to be given these many a times. We're not going to have to find the A and the B. But the way this works is it starts off with very rapid growth, kind of like an exponential function. And then it reaches this point, it's actually called inflection point, where the growth still increases, it's still going up, but it starts to level off to this maximum value. One area this is used a lot is in stores. Very famous example of Walmart, Sam Walton, understanding this. And he would be able to track the growth. And many stores, when they would see this, they would say, oh, still going up. We need to order more stuff, buy more of whatever. Sam Walton, took math class in college, realized once I hit that point, it's kind of changing shape. It's starting to level off. They would stop buying. So Walmart wouldn't be stuck with extra merchandise because they understood this idea of a logistic growth. Things don't usually grow exponentially. Long term, they grow logistically. So let's look at an example. Another example besides selling goods in a store, spread of a virus. This is how a virus spreads. The number infected. How many are infected after 10 days? Well, to find how many are infected after 10 days, all we need to do is plug 10 in. E to the negative 0.8 times 10. And if we do that on our calculator, 5,000 divided by 1 plus 4,999 e to the negative 0.8. Once again, be careful on exponents. And our number is 1,867.8. Now, if I graph this, let's graph this for a second. 5,000 divided by 1 plus 4,999 e to the negative 0.8 times 10. And if I graph it, I'm going to go 0 to, let's go 5,000. I'm guessing here, we'll see if this works. Too far. Let's go back. Let's go 500. Nope. Oh, there's the problem. I put 10 in. I don't want 10. I had no variable. Need X. There we go. That's much better. Now let's change our window. Find our graph. There we go. So if you look at the graph, and I might even change that a little bit more. Let's go 0 to 50. 6,000. There we can see it even better. Now you can see what happens. It ramps up. It gets to about this point and then slowly starts to level off. And you can see it levels off. To figure out what that value is, if we hit trace, you can see we level off really close to 5,000. So if this is infection, we can see that, if you think of the graph, it starts off more and more people are getting infected, and then it levels off because most people have the virus. Gaussian normal distribution, bell-shaped curve. We have this formula. We get a graph that looks like this. And the way it works out, if this formula is our formula that gives us the height of men in the United States. If we want to find the average, that's just going to be our maximum. So our max is the x at the max point. This is one application. Those of you that in statistics, we'll get to this later, so I wanted to just bring that up here. So all you need to do on these points is just graph them and find the max point. Another one, logarithmic model. Here, we can model things with natural log. Two things that are based on this kind of model are the Richter scale and pH. Both of those are based on the logarithmic scale. Now, both of them actually are based on log base 10, the common log, and there's reasons for that. Just to kind of give you another example. The last problem we're going to look at is Newton's law of cooling. And we're going to look at an example. Newton's law of cooling says, at 8:30, a coroner is called to the park where a person was killed overnight. In order to estimate the time of death, the coroner took the person's temperature twice. At 9 o'clock, the temperature was 85.7 Fahrenheit. At 11 o'clock, it was 82.8. From these two estimates, estimate the time of death given the formula, where T is the time since the person has died, and T is the body temperature. The formula assumes the normal body temperature is 98.6, and the air temperature, is a constant 70. So let's figure this out. So at 9 o'clock, it was 85.7. So let's figure out our time. Minus 10, natural log, 85.7 minus 70 divided by 98.6 minus 70. You can see here this constant temperature 70 goes in the formula there. Normal body temperature goes in the formula there. So let's evaluate this then. So we have negative 10 natural log 85.7 minus 70. And notice how I'm using parentheses to try not to make a mistake. And we get 5.997. Now, we're going to do the same thing, but 2 hours later, when it was 82.8. And we want to figure out What's the time later? So now we do the same thing, but I change my formula. To 82.8. And I get 8.03. So how does that help me determine when the person died? Well, at 9 o'clock, it was basically 6 hours earlier. At 11 o'clock, it was basically 8 hours earlier, which makes sense. 11 is 2 hours after 9. So if I go back 6 hours from 9, or 8 hours from 11, I get 3 a.m. That is the time the person was killed. If we want to estimate the body temperature after 2 hours, now we know 2, and we have to figure out T. Now this becomes just a exponential equation. I'll divide by 10. This is T minus 70. I can subtract the bottom as 28.6. And now I can say E to the negative 1/5 is equal to T minus 70. I can multiply E to the negative 1/5 times 28.6 plus 70, which is what I had to go through to solve the equation, and get 93.41. Which makes sense, because at death it was 98.6. 2 hours later it's dropped a little bit. 6 hours later it's dropped more. And then 8 hours later it's dropped more. All right. Homework. Worksheet. Applications of exponential functions.